Balance and stability is something you probably have quite a good understanding of already, so I'm going to go over the key points quickly and then focus on how we can explain toppling clearly. Let's start by defining the center of mass as the point at which all of the mass of the object is considered to be. Obviously, the mass is spread out around the whole object, but this idea of center of mass makes the maths much easier, and it works. Interestingly, the center of mass might not actually be in the object, like for this horseshoe, for example. Let's also define stable. In simple terms, a stable object is not likely to be overturned. Here's a nice example. A wide box with center of mass here. Clearly it is looking nice and stable with its low center of mass, wide base. But can you explain, like properly explain, why this is stable? Not just, oh, it's got a wide base, but why does a wide base help? Pause and have a little think. Okay, I really hope you had a think about that. Here's one way of looking at it. I'm going to overturn this box like so. Okay, so I've got a few diagrams there showing the box changing from one position to another. Now let me draw the center of mass in on each one and join the dots. See how the center of mass has gone up, and that's going to require energy, isn't it? Also, see how it went down again a little bit. That means going in reverse would also need some energy put in to lift the center of mass, but not so much. It's more stable when flat because it needs more energy to overturn it. When it was standing up like that, you have to put some energy in, but not so much. It's less stable. Right, well, that's much more detail than you need, but it's all good stuff. So what about toppling? Can we describe it? Well, let's take this drawing and think about which way it will topple. It's pretty obvious, just looking at this simple example, but it actually all comes down to moments if we're wanting to explain it. The center of mass is where the force acts. Like so. And the corner here, the corner where the object is touching the surface, touching the floor, that's the pivot. So there's only two forces. The ground pushes up at the pivot point, so D equals 0 here, so the moment there is going to be 0. The only other force is the weight, which acts at the center of mass. This here is the perpendicular distance. So that means I've got an anti-clockwise moment. The box turns anti-clockwise. Since turning anti-clockwise will mean it stays in the original position, it hasn't toppled. If we lifted it over this far, now the moment is going to be in a clockwise direction. It's going to go and land into a different position to the original one, so we can say it has toppled. So now we have an understanding of why wide bases help stability. And the same is going to be true for a low center of mass. We also got an idea of how to predict whether something's going to topple. Simply put, if the center of mass is between the ends of the object, between the two pivot points, then it will not topple. You should also make sure you understand how to find the center of mass of a plane lamina. There's a simple experiment for doing that, and that is stability covered.